So I'll be doing the talk in English, actually, so sorry for that. I'm a business developer at TNO in the Netherlands, and today I'm going to talk you through about the activities that are ongoing at TNO in the space of quantum. So before I delve into the topic of quantum, I would like to first briefly introduce what TNO is, where I'm coming from. There are many research and technology organizations within Europe. We call them RTOs, such as VTT, IMEC, Fraunhofer, CRLAT. TNO is one of them. TNO is one of the largest RTOs in Europe. And the main task of an RTO is to upscale the technology from an academic level to an industrial level. So we form the bridge between academia and industry and bring more promising technologies into the market. Within Netherlands, we are located in many locations. We are almost close to 5,000 employees now as of 2025. We hold a broad patent portfolio, as well as we are close to almost 1,000 public-private partnerships. And in addition to this, we also have a base, I think, in Japan as well as Korea. Now coming to profile in units of TNO, as I mentioned, TNO stands for Netherlands Organization for Applied Scientific Research. It has 6 units within it. It was established in 1932 by the so-called TNO Act. We are also trusted advisor to the government. We are also non-profit, non-commercial organization, so we really try to help startups, scale-ups, big tech companies with research and development efforts. But we don't commercialize ourselves, the products. When you talk about the technology readiness level, we operate anywhere between TRL level 2 to TRL level 7. Low TRL level, is quite obvious because these are the new technologies that wants to come to the market. But we leave the fundamental, fundamental research to academia. We also work on very high TRL level, let's say TRL level 7 or 8, because you can imagine that there are already mature technologies in the market, but still they need further improvement. So just to give you an example, we have had almost 25 years of partnership with ASML and Carl Zeiss. You might have heard about these companies in Europe. Who are working on extreme ultraviolet lithography systems, and we are trying to help them improve their optics lifetime of their EUV mirrors. We operate in almost 3 models. Public-private partnership, which is quite obvious. We set up joint innovation centers, as well as we are part of big European projects. We also act as national lab for the Dutch government, so we get some specialized tasks on specific topics from Dutch government, such as conducting geological survey of the Netherlands. And we also do contract research for customers, which are fully paid by the customer. And we prefer this route also because the time to market is very short. It's a very tightly knit collaboration. When you talk about strategic collaborations, we do that. We have done this many times in the past. We do this to develop critical knowledge within Netherlands and within Europe. QTech is just one example of that, which was established 10 years back, which was a collaboration between TU Delft and TNO with the aim of developing prototypes of quantum computer and quantum internet, which was at that time very low TRL topic, but now things are getting more and more mature. It's going towards commercialization. So we are trying to provide engineering expertise to help them scale up. And we are also involved in creating spin-offs. So we have done this many times in the past to generate economic impact from research. Orange Quantum Systems and near-field instruments, you might know, are really coming from TNO, whereas companies like QBird, Quantware, and QBlocks are coming from QTech. Now, that being said, let me switch gears and talk about quantum activities. So within TNO, as I mentioned, we have 6 units. I'm coming from the high-tech industry unit. We are more hardware-driven people. We work on quantum devices, materials, quantum computing, quantum sensing, as well as quantum communications. Whereas our colleagues in defense are working with Ministry of Defense on quantum sensing-related topics. Our colleagues in this unit are working on higher-level stacks, so quantum applications algorithms. Quantum application lab is one example of that. Interfacing classical and quantum networks, post-quantum crypto, as well as ecosystem development and strategy consulting. Now, when you look at the high-tech industry unit where I'm coming from, it's a group of 70 FTEs, highly skilled engineers and scientists who are working, which bring in different competencies such as material and device fabrication engineers. We have system integrators. We have scientists who do chip device characterization, chip testing, as well as system design, or chip design and modeling as well. And in terms of facilities, we have clean room facilities in Delft, as well as quantum computing lab, which I will talk about in the coming slides. In view of the time, I will only limit to these two topics, whereas we also have quantum internet as well as quantum sensing lab in Delft. Now, coming to the topic of discussion today, there are many challenges that goes into, or there are many challenges that are required to build full stack systems. There are many layers that goes into full stack. Of course, as you might know, at TNO in high-tech industry unit, we are mostly working on the lower level stack. So really the physical layer, because it's already very complex, very cumbersome. But we're also working on the stack integration as well. So we take a lot of parts from different suppliers and put everything into one stack, basically. So just to, on the topic of quantum device development, just to list down some of the challenges that we normally face, which is very cumbersome. It's non-trivial totally. But I've just mentioned few of those here. There are many challenges, of course, in the market as well. So, quality of quantum chips. So how you make your quantum chips in the first place, the materials impact your qubit performance, the material interfacial defects that can also influence your qubit performance as well, scalability to be able to design your chips in order that they can scale, especially when you go to larger arrays. Addressability to be able to address single qubit in multi-qubit operation, meaning that you reduce the crosstalk, measurement standardization, stack integration, etc. Some of the challenges we are already working on within TNO, whereas some of the challenges we rely on our partners, such as Q blocks or quantum machines to provide us with control electronics, as well as cryogenics, let's say Blue Force, who provides us with that. Now, having mentioned the challenges, I think it's also important to look at the value chain, how the value chain of quantum computing looks like. So what I've done here is sketched quantum computing value chain for spin qubits, but that is also quite relevant for transmon qubits as well. So there are three segments here. There are three segments here, the QPU fabrication, the device characterization, the middle part, and also the stack integration, the right part. So what you do essentially is that you do a chip design. You take your materials of choice. For example, you do quantum device fabrication in clean rooms. After that, you do large-scale device characterization, and from that, you select some of the devices which are outperforming, and then you do more in-depth qubit characterization, and then you select the more promising devices and put that into a full system. Within that, it's not only quantum devices. You also have control environments such as cryogenics, cabling. Cryogenics, for example, you also have cabling, input-output signal propagation, low noise amplifiers, 2-pass, for example. There are companies who are working on control software such as Q-control, for example. And there are companies working on control electronics such as Q blocks or quantum machines. So we put everything into one stack. Now, so what I will do in the remainder of my talk is to go through each of these blocks, primarily and really tell you what TNO is doing in those spaces. So as you can imagine, when you talk about chip design, it's very non-trivial, especially when it comes to quantum, because quantum states are fragile. They can decohere very fast. So it's important for us to also understand what is the underlying mechanism that leads to this kind of decoherence or this kind of behavior. So for that, we have a working group within TNO who is extremely experienced on chip designing. So we have experience with resonators, parametric amplifiers, 2-pass, for example, superconducting antennas, squids, transmon qubits, as well as spin qubit systems. And just to mention this here, that TNO is really experienced in transmon qubit and spin qubit systems. So the lab of Leo DiCarlo in Delft has been actually using our designs to make their transmon qubits. And they use these kind of softwares, and they're very proficient at it. So once you have the chip design, what you do is to do actually the device fabrication in clean rooms. So this is what we do. This is again for spin qubits, but can be also extrapolated to many other quantum devices. What we want to do within TNO is to close the loop between chip design, chip fabrication, and chip or device screening or characterization in order to really close the circle as much as possible, to really have rapid feedback loops and do rapid prototyping with very short lead times. And what we do is, you take as I mentioned, we take the materials from supplier. We do first, let's say, the large-scale devices to really characterize the materials. Once that is characterized, then we do quantum dot or quantum device fabrication. We test the devices into in our cryo fridges, and then if everything looks good, we load the device into our full stack system called Quantum Spire. No, in case you might be wondering, what really we are working on, which topics we are working on. So this is a schematic of that for sure. Just to summarize it, we are working on transmon qubits. As I mentioned, we are non-competing organization, so we don't do the fabrication of transmon qubits because there are already players in Europe such as Quantware who are already doing that, but we do the design and chip testing. We do also fluxonium qubits as well, but when it comes to 2-powers or resonators, we are fully integrated. The same goes for spin qubits. We are fully integrated there as well, so we design, fabricate, and also measure the spin qubits. We have scaled our activities down in topological qubit space, but we are really active on quantum devices in diamonds, especially based on NV centers and tin vacancies. Okay, coming to the middle part of the value chain, which is about in-depth qubit testing or device characterization. So for that, we opened this facility called KIT, which really acts as an enabler for B2B and European projects. This was opened in 2020, which really became a workhorse for many European and Dutch quantum ecosystem. And within this facility, we have a range of facilities or systems. We have 2 dilution refrigerators, and now we are procuring one more, so which will allow us to measure up to 36 transmon qubits and up to 10 spin qubits. We have 1 Kelvin system, which is focused on high throughput device screening and device characterization, and also electrical component characterization as well. Then we have 4 Kelvin system, which is focused on defect characterization and material characterization. And then we are trying to procure 300 Kelvin system, a room temperature system, which is for automated device characterization at room temperature. Now, as I mentioned, KIT plays a key role in many European projects, and so we are part of many European projects, of course. B2B projects are very confidential. So we are part of QTest QPilot. I'll be briefly talking about that, not going in depth at all. We are part of QTest QPilot European project, which is focused on distributed infrastructure within Europe for chip testing and device fabrication. We are part of ARTIC with the aim of developing large-scale characterization of spin qubit devices as well as electrical component devices, Then we are part of QLSI2 with the aim of developing prototypes of spin qubits on 2 material platforms, silicon germanium and FDSOI wafers, and then move them into production once 200 qubit system has been demonstrated. Then we are part of Open SuperQ Plus with the aim of developing full-scale system based on 1,000 transmon qubits and then make it available for external users. We are part of CHIPS JU pilot line proposals within Europe, so working on many pilot lines such as spin qubits, transmon qubits, etc. And then we are also part of USPC European proposal. And with this in mind, the reason why we do this is because we want to develop critical knowledge and use that critical knowledge to really enable the Dutch and European ecosystem propel further. Last but not the least, of course, it's Quantum Spire. It's on the right side of the value chain. It was the full stack system that was fully designed and engineered by QTech. That was already established in 2017. So it has been some time now. Initially, it was based on 2 qubit modalities, spin qubits and transmon qubits. So it was earlier 2 spin qubits and 5 transmon qubits. But now we are scaling it up to 7 or 8 spin qubits actually and 17 transmon qubits. So with this, I would like to summarize my talk in some propositions. So as I've already mentioned, we are working quite a lot on device designs and simulations, device fabrication as well on different types of devices, material inspection. We also have KIT facility to characterize the devices at different temperatures. We also do in-depth material characterization as well, and we also provide consulting services for people who want to build their own full stack systems. So with this, I would like to thank you for your attention. I'll be at the Netherlands lounge or Netherlands booth, basically. So if you are interested, please feel free to reach out to us, and I'll be happy to answer questions.